I'm going to recommend working on this in a kind of a split screen format. So that'll look something like this. The idea is, again, here we're not trying to completely reinvent the wheel on everything. There's a number of things that we can do with these, and depending on their different kits, they will have specific ways to attach them. Some of them, when they go to actually build the physical prototype, it's going to look very much like this, and you just replicate exactly what you're doing in Tinkercad on the actual physical device. Some of the kits I think are going to have headers soldered directly on them. Some of them I think are actually going to have a potentiometer built in. This is assuming that they don't already have the potentiometer. If they do, they're going to have to change just ever so slightly how those are hooked up, because some of those pins that we're going to look at as far as the actual connections and other things, some of those aren't going to be as obvious. The potentiometer is needed in order to set the contrast on the LCD, so let's take a look at how to actually set some of these things up. So some of the things that we can tell even before we get into anything fancy is we're going to set up the breadboard and the Arduino. So we don't need a full-size breadboard, but we do need an Arduino. So most of the time we're going to get away with using the mini breadboards, and it's no big deal there. I'll zoom in here in a little bit on this once we know we've got most of the parts that we need. We don't have to have an external power supply because there's nothing too crazy going on. One thing that we do need is we do need a potentiometer on the board. So I'm going to go ahead and set this guy up. You know what? I'm going to set him up up at the top of this board. There's a couple reasons for that, but I'm going to leave it at its current impedance. The 250K is fine for now. What we're going to do is use that in order to set the parameters for our screen. So down here we have a screen. I think it's actually under the all components. We can just expand this and grab ourselves a display. Here it is. So because of the wiring and the way that it'll need to go, I'll recommend something like an offset like this maybe. So having our Arduino set up here, I'm going to drag this up, give us a little room to do kind of some wire management. This will make it just a little bit easier. If you just set this into place, it doesn't necessarily assume connection with this, because if you have something connected, it will go in and highlight these, but this isn't necessarily assuming connection with the board, so I found that I actually have to hardwire it. So that can be a little bit of a pain, but if you do it kind of down here out of the way, it makes life a little bit easier. So some of the things that you can do initially for your setup is come around here and ground both sides of the board. The downside of doing everything back to back to back to back is it can make things a little extra chaotic. So I'm going to leave that one there. I'm going to make that one a red wire just because I like to use some sort of normal wiring convention. All right, so our 5-volt is what we're going to bring in to the board. So we're going to run that. This is going to be a red wire, and we're going to run a ground to our black. So all of those rails now, once this is powered up, will be energized. So there will be a couple other pieces that we're going to need. There's some connections we're going to zoom in here in a second that are really obvious about how it's set up. There's some that are a little less obvious. A couple places where you need to have at least one place where you need to have a resistor, because this is LED backlit, so just like regular LEDs, you need to have some kind of a resistor in place. On the backlight, we're going to have a couple other wires to tell it that it's enabled. We're also going to grab our thermistor. So I think that's actually up here in the group of sensors. Temperature sensor. Here we go. So we have a temperature sensor and that's what we're going to be using as our reference point. So this is, yeah, this is our temperature sensor, so we're going to be using this in the board somewhere. I think I'm going to set it up over here somewhere just for the sake of continuity. So we'll take a look at how to connect that up in a little bit, and it goes through and tells you what the pins are. So the voltage out and the ground. So this one is a temperature sensor, slightly different than a thermistor, but it's still giving you a difference between the voltage out and the power. So fairly straightforward in terms of actual use, and that keeps things fairly simple. So we'll go ahead and connect up our ground while we're here, just because that'll keep things simple. And we'll connect the V out here is what's going to end up going out to our system. Power we're going to run, as far as I know, this one can run off of 5 volts, but we will find out here in a second if it catches fire. So this one, normally, if a component is not spec'd for that level of power, if it needs 3.3 instead of 5 volts, more often than not, it'll do this. So if you, for instance, hook up, and this is something that's important to help students with, we have an LED, and we have a 9-volt battery. I haven't actually used the lemon battery. I'm sure it works just fine, but for this, if we just hook up 9 volts to our LED, what it's going to do is say, hey, this is 915 milliamps. This is going to cause a fire. Fire is bad. Fire is how you smoke out your dorm rooms and set off the smoke detectors. No, I'm not giving you guys ideas. In fact, don't do that. That's a very bad idea. But the idea is you can show students that you've got a little bit of logic built into this system. I'm just going to go ahead and delete these components because we don't need them. We don't need an external power supply for this particular project. So there's a couple things that we need to be able to have hooked up. I'm going to leave myself a little more room just for cable management. So the first one is going to be ground. Fairly straightforward. And what we're doing is we're going to start building this circuit that they have in the tutorial here. So they give you a parts list. This is exactly the same kinds of things that we're going to be using. Potentiometer, 100 kiloohms is perfectly suitable. Few hundred kiloohms is the default resistor, or is the default resistance for potentiometer. So long as we've got enough current going to that backlight, you'll still be able to read it. So we have an Arduino Uno, and they have all these kinds of kits in their system. So this one specifically is a tutorial for a thermistor. So this one is a slightly different part, but this will give you, as near as makes no difference, this has a ground reference. So this one is a little bit more sophisticated than a thermistor. A thermistor is a simple 2-wire. It's essentially power in, voltage out. So it just acts like a simple resistor instead of having a reference state. So this one's a little bit more sensitive, probably a little bit more accurate, but this walks through kind of the equation, so you can spend some time talking to the students about that. You can also spend some time talking to the students about how the equation works. So this difference between the voltage in and out has to do something with the scaling of the resistance. The resistance changes as a function of temperature. So as stuff gets hotter, the resistance actually becomes less and less. The amount of power that's consumed changes, and so on. So this is some of the examples of code, and they give you 3 different sets. So this is for serial monitoring. So if they can't figure out how to get their LCD display to work, if they can't figure out some of these other pieces, the idea is we want to point them in the direction of tools or examples they might use as a reference, and help them troubleshoot when something isn't working or isn't set up. So this one is for serial monitoring, so putting output back to the computer is what the serial monitoring does. So they set up the baud rate and look at setting up variables for temperatures and some of those things. They do the temperature function as a function of resistance, so you need to know the total resistance of the two for the thermistors. Similarly, you've got examples where you're using the LCD for the output. So this is probably the one that I recommend the students try and work toward, because the LCD is going to give them the most useful information, and that's what they're going to be able to kind of hold in their hand as they're walking around. They just probably have it set up in their cardboard box or something. Because you can power the Arduino off of a 9-volt battery or all kinds of other things, as far as the board is concerned, there's no real difference between powering it from USB versus powering it from a 9-volt, because it's still got a voltage regulator right here on the board in order to make sure that it's got good clean power to run off of, and a little and they've got a couple other things that the board does as well. So there's a lot that we can do with this, but this is essentially the model that we're going to be working with. So this is actually really most of the code that we need. They also develop in this the code for converting back and forth for Celsius to Fahrenheit, because we want to try and, again, build off of all of the stuff that we've been teaching the students about units, about number management. In this case, we have to do a lot more wire management and all of these different things. So we have to set these up and say, okay, we need to understand, we don't need to understand how to author all of this code from scratch. That's not the goal of this class. The goal of this class is how to take some pieces that are already developed and use them for a different way or a different method, a different project. And so you're working with modules or pieces that are already developed and just using them in a different way, or using them for something new. So this goes over converting back and forth between temperature in one scale and another. So you can do temperature in Fahrenheit as well as temperature in C, and this outputs back to the computer, I think, is the way that this is set up. So this one, I guess all of these are set up to output back, and I don't know how well the serial functions work in Tinkercad, because I haven't actually tried much with serial commands. I don't know that it actually looks at signal coming back from the Arduino in the same way, but we'll take a look at this. So the readout for the LCD is what we're going to focus on. So this is as near as makes no difference, this is our starting point. So for the code, again, I always switch back over to text. Yes, I'm sure the universe won't explode. And what we're going to do is we're going to drop in our code. This liquid crystals library is one that actually includes a number of these functions fully defined, so they don't have to worry about calling functions specifically for the LCD display. This is just including those, and you can have class discussions about, well, why would you want to do that, and all of these sorts of things. These thermistor pins, so this is setting it to be pin 0 is where it's going to come up, and we have a variable v0. We have a resistance that's tied to 10 kilo ohm resistor is what it looks like that's set to. We have our couple other variables. These are all floating point variables, specifically for the number of the precision for memory storage as far as the Arduino is concerned. So how many decimal places, that's a floating point number as opposed to an integer value of 1 or 0. So again, all stuff that you can talk to the students about, but we don't want to walk through and give them step-by-step instructions on how to complete everything, so much as we want to help troubleshoot when they're stuck on something. So we really want to focus again this semester on trying to get them to own the learning experience and get them to understand that it's not as much our job to understand information for them and then tell them exactly what's going to be on the test and whatever other crazy ideas they've got in their head. It's our job to teach them how to think about and how to approach doing something that they've never done before. So how do you problem solve? You start with looking and seeing, has something like this already been done, so that I don't spend the next 20 years trying to figure it out, right? So same kind of thing that we're going to do here. So this is going to read the thermistor pin in, and then it's going to print the temp out. So this is the code, lots of different examples. And this is part of why I suggest, for instance, reading or coming to the project hub. Lots of great examples, and they do a really great job with their write-up. So the first part of the enclosure is the thermistor, so voltage in and out, the signal pin. It'll work essentially the same way for this. So the signal pin is what we're going to route. So this is actually going to come, I guess I'm going to route this up and over. So this signal pin I'm going to bring up and over. In their case, they're using analog in 0. So that is this one. So I want to leave this one orange as our signal pin here from the voltage out to the analog in. So it looks slightly different than what they're going to have. This is more like, this is essentially contained within the temperature sensor, this difference between a resistor and this temp sensor. So I'll have to look up and see for making the code work in this example. Since I don't actually see the actual thermistor in this list. That's kind of a bummer if they don't actually have the thermistor, because I was sure they actually had one in this, but maybe they don't. Yeah, doesn't look like it. Huh. Okay. So anyway, I'll have to look at modifying the code to run this particular temp sensor. I'm sure that this one is also used very heavily. So this code is set up to work as it is right now with their the same physical hardware that they will actually have in their kits, which is good. I think it will. I'll just have to be careful about the reference value that it's using for the impedance. And that's really what it comes down to. So this one, I think, houses that resistance internally, so I'll just need to look at the data sheet for the TMP36. But again, that's another good exercise for students, is looking at, okay, well, this is still a temperature sensor, but it's different from a thermistor. Why? How? Is it that it's internally housing this resistor? That's, again, discussion points, thoughts that we want to have for the students to be covering in what they're working on. So, once that combination is set up, so I'm skipping that particular resistor, bringing it in, so we're still supplying 5 volts to the thermistor, and we know what the reference value is for ground. So this is a simple example for the thermistor, what it actually looks like, and that's pretty cool, actually. So then when we go to the next step of how to do this, like here's an instance with the temperature sensor specifically, actually, so I don't even have to go to the work of modifying my own code here for running this. This is an example where it's shown in Tinkercad, and again, I've not had real good success with just kind of setting this onto the board and it assuming connections. I've had a lot of issues with that. So here, we're not adding an external resistor. There is a resistor for one of these pins here that is the LED pin. So the LED anode, this is the LED cathode, so cats are bad, that's the negative side. So we'll put we'll go ahead and put a negative in here. But what I'm going to do is I'm actually going to run the resistor off of the negative side, just because I think cats are a evil force to be resisted. So this is set up. So now we have the anode. This will be the positive side. So this is actually going to be wired up and over to our this one. So no, the contrast is going to be wired up. Contrast is going to be wired up separately, so that's not included in this picture diagram, or in this diagram. That's not included. So he's got he's not running a potentiometer at all on this. He might be running just a straight resistor. And I mean, that's one way that you can do it. For the sake of continuity, I'm going to bring this over here, and I'm going to bring this down to the lower level, actually. So whatever comes in, this is terminal 1, that's the wiper, and terminal 2. So terminal 1, this will need to be between the positive and our LCD. So I'm going to do this as red. This one I will also do as red, just for the sake of continuity. This will jump across. Okay, so this is going to come in across our wiper, terminal 1 and terminal 2. I'll double check that wiring arrangement is correct when we get power hooked up. So here we see we've got contrast. As we change this against the wiper, we get less contrast because this side is no power. This side is running 12 volt or 5 volts in, so should be good there. Again, good kinds of steps to encourage the students to do along the way to make sure each of these pieces are working individually rather than trying to connect everything up all at once and then troubleshoot the whole thing. You always work in pieces in order to make it work. So that's also helpful. So in this one, he's running the input for Vout into one of the same thing, analog 0. And he's got the code here. So similar setup. He's doing the conversion to C based on printing Fahrenheit. So it's the formulas in many circumstances, depending on what you're using. The formula is going to be determining in C, so you can display one number in C, pause, display the second number after converting it in Fahrenheit, and that's probably the way that I would recommend having students see what this is. But this is on his cardboard or whatever it is that this is on. This might actually be on a little larger hardboard. He's got that mounted up, but in essence this is what I'm trying to get students to build and then walk around their house with, apartment, tent, living quarters, dorm, whatever, and get some measurements at some different places, measure the air coming out of the air conditioner, measure the air elsewhere in different rooms, and see if it's the same exact reading everywhere in the house. Spoiler alert, it's not going to be exactly the same reading all over the house, and that's part of what we want them to learn from this. So he doesn't have another more detailed diagram for this, but now we have to set up a couple of the other things. So for this one, power is pretty straightforward. So again, I like to get students to start thinking about wire management and make it clean and organized, because it takes a little bit more time. But if you're bringing just raw voltage in with no signal, using something like a red wire is sensible. In this case, this one is a varied signal, so maybe it's better to use, yellow or something else. So then there's a few others. Contrast, register, read and write pins, the enable we're going to have to wire up, and I have some other examples that I can show you of circuits where this is very well done. This one doesn't go through and detail the connections as well, I don't think. But you can see a couple of them. So what this is going to do is, again, assuming that we have a potentiometer set up, some of the boards may or may not have a potentiometer and some circuitry soldered onto the back side of the LCD. I think most of them will not, but some things could have changed between now and the future. Hopefully we still have classrooms, and this isn't being viewed by some historical society after the end of civilization as we know it. So I have some other examples that I can show where the LCD hookup is a little bit more clear. There's also a lot of really good tutorials set up where this is very clearly outlined for how this gets hooked up and to which pin. So this one, I think, lays it out a little bit more clearly. Here we go. So there's a couple pins, and this is an actual circuit diagram of sorts. Works well enough. So the Arduino Uno is the Rev 3 is what most everything uses. Is what's in all of their kits. So there's a couple things that we need to do. So the voltage signal and read-write can go together. So the voltage signal here, so the power in, we can connect to the read-write. So we can set this up just as a jumper. I'm going to set that up as a turquoise jumper just to be a little different. So this VDD, or this is the VSS actually. So this is VSS. This is set to ground. So I'm going to move this jumper over to ground where it's supposed to be. Good catch, those of you that are shouting at your TVs and computer screens. So this read and write, that's an enable signal. So this one can go to enable for pin 11. This one, so enable, can come up and over to pin 11. This is where, again, cable management becomes very helpful, because we can see exactly where this is headed. Let me see if I can get it to move. Nope, not without disconnecting. So I'm going to move this up a little bit. So enable needs to come up here and be connected, because if students just connect wires and it's going across their screen everywhere, it's going to be a mess. Nobody's going to have any idea what pin is supposed to do which job. This one I'll go ahead and leave green. So this hooks us up to pin 11 for enable. Couple other key connections. We can skip for most of these DB0 through DB3. So if we zoom in here, DB0 through DB3 we skip. DB4 is where we start making connections. So this one is probably easiest to set up. Probably, so it's in a reverse order because of complicated reasons. 7, 6, 5, 4 connect to 2, 3, 4, and 5 for digital write pins. So 7 comes up here. This one you can see we're going to want a different color. And I'm going to move that just slightly. So I'm going to be in the same boat here. There we go. Just trying to make sure that the numbers and values are still visible enough for you guys to see what's actually happening here. Okay. Bring that in a little tighter. So this one is DB7. That should go to digital pin 2. I'm going to make this a blue wire. So the wire colors also start to matter, because if you just have a mess of green wires going everywhere, that will make life very hard. And depending on what you have open, you can collapse this out of the way to give you a little more working room, since right now we're just doing essentially wire routing and cable management. That keeps things a little more simple. So then same thing, DB6, DB5. I'll go ahead and pause this for a second and finish up cleanly routing those, and then we'll jump back in so that you can see what's actually happening here. And we're back. So I've done a couple things here. The main things that I changed is just deciding to hook up the LED backlight to constant power instead of kind of using it as a variable brightness. So I set this up with the potentiometer for contrast. It's just a little bit cleaner way of doing it. The only one now that I have to finish is this register select. That one I'm going to go ahead and set up now. So I have this set up in such a way that I can come back up over here and we can use pin 12. Yeah, that's a reasonable place to put it. Pin 12, register select. I'm going to do this one in yellow because I don't have a lot of yellow. Okay, so there are a few things that this will do as kind of the standard hookup, and you can clean up the wire routing even more than this. The idea is just to show you everything that's required to get the LCD to be functional, to where you can start playing around with the temperature conversion, the actual measurements, and what's going to be involved. So I decided to go ahead and use their same potentiometer arrangement for the contrast, just because what that allows you to do is instead of bringing the brightness up, you can change what the signal looks like. And so in this case we needed more contrast just to get the signal. So the temperature right now is saying 4.46 Fahrenheit. So this is already functional using the code. Now, whether or not the temperature is in fact 4.46 Fahrenheit, the point is we've got all of the componentry working at the moment using the same output pins. So all of the code, if we're looking at it here, I'll go ahead and expand this over since you don't need the diagram now. And you can inspect our beautiful work here of the shiny crunk jarv, whatever that is. They always try and make sure that there's no copyright violations in any of the gobbledygook that they put together for names. So again, same fundamental three things that we're always teaching them and reinforcing about the Arduinos is you start by initializing. So tell your variables what their names are and where they're starting, and then you set up, you include the liquid crystal library for this particular one just so you have a working display. Then you set up, so you tell the pins what their names are and what they're starting at. Then you start setting up, those are all the other variables and things that you initialize first. So always initialize, then you set up. So what's it actually going to do? This is set up for serial communication. Then you set up the actual loop. So this is doing analog read, and then we do print to the LCD. So it's just saying temp, return, and then Fahrenheit. Or actually we're not even doing return. So then you print the value T and then the number F. So if you wanted to double slash is comment in Arduino. So what we do is we change the value. We convert from Kelvin to Celsius. Now we run it, and we'll see a value displayed in C, or we should here. So we're still pulling the value T, and it should be, there we go. So this is why I say the temperature is not quite correct, and this is why you need a potentiometer, is sometimes it can boot up even if it's set at the right value. It doesn't know that it's always set at the right value. In the simulation, in the real hardware, you wouldn't have this problem, but blah, blah, blah. Difference between real life and simulations. The point is, this way students learn how to do things and not smoke all of their components, because smoking is bad for you, whether it's electronics, vaping, or any other variant. This is what we want them to be able to see. Now in this case, minus 15, is that actually what we're starting with? Not quite certain, as I don't know offhand what that part number's internal resistance is. For this example in the code, he uses, I think, a slightly different value effectively. No, maybe he's using the same 965. Yeah, maybe he's using the same 965. So in this case, our temperature, I'll go ahead and correct this since I've got all of you live and all of this is super riveting. This gives us what? So V0 minus 1. So our scalar he's using instead combines a couple of those steps as a different formula. So yeah, one of the easiest ways to do this is, this one is not solved for the same value. So this is all looking at millivolts. Okay, so this is I like the approach of this a little bit more cleanly. You're ultimately doing exactly the same thing, but this is just taking a logarithmic approach for a thermistor as opposed to this temp sensor. So the temp sensor has an internal value that's taken into account in this formula. And I'm assuming he's using the same part number, but it's pretty hard to tell. So yeah, this is probably a cleaner way to set this up. So what you can do for the purposes of this is replace the loop here. Actually, I only need this one. So this we can replace, once we stop the simulation, we can replace it with this. So this does the same kinds of things. The only exception is we're doing a digital write to, in this case, he's doing a digital write to P is 8, because I think that's how he's got his hooked up. Yeah, I think that's how he's got his hooked up. So ours for enable, is he using the same pins on this? He's using 1211 5432. So okay, so he is actually using the same ones. The only thing he's doing differently is we haven't defined P in mode P. So for 8 he's using output, which is 7, 8. Yeah. So he's actually using 8 as, I think, his read and write, or his register select, rather. But again, because of the way that he's got this wired up, his read and write, or his register select, is not set up to 12, but it's really hard to tell for that one. So this one is, yeah, digital write to, in our example, we're doing digital write to this code set, second one. We're doing digital write after an analog read. We're just doing a print. So actually, we don't need to set this to be low. So this, I don't actually need to do a digital write at all there. This is some of the same kinds of things that we want to pull in. So analog read, his variables are different. This is part of the fun that I want the students to go through. So this is actually a good exercise for instructors to go through as well, of altering the code for the different variable sets that you're working with. So this, when he's looking for temperature of this one, you're gonna have to run his variable set as well. So the only difference is, so I'm gonna go ahead and copy in this portion as well, just because of the number of pieces that he included here. This way the pin assignments will be the same. So this one, closing the loop, and P is defined right here for the pin mode. So this is an interesting example where this one, okay, so this is a case where he's forgotten, or when this copied over rather, this did not include the close for the setup, and that causes issues with the void loop. So drop out of the code window, open that back up. So it should get rid of the orange bar here because there's no longer a problem with this. But same sort of idea. If it were to be reading something like 85 Fahrenheit, that's actually more what I would expect the value to be. And so that's why it's important for students to see what the differences are. So in this case, if I said, I'm going to alter this now, and I say, I want to comment this one out, and say, nope, not this one, I want to comment out the one below it, we can print C, and we can do a print on C. So by changing those variables and commenting that out, what we get is a value of 29C. So it's actually very simple to incorporate the code. The challenge then is to get students to think about, okay, well, how do I get it to display one and then the other? How do I get it to display units and tell me what the number is? Because a number without units and without some sort of variable name doesn't really mean much, right? So we want students to figure out, how do you modify now what this code is doing in order to do all the cool things that we want them to do in the lab. So hopefully this gives you a quick example, or a quick walkthrough of a couple things, including how you set up the basics of an LCD, and you see why it can take a lot of time, like most of a full class period worth of time outside of class, maybe even longer than that, for students to actually do this completely from scratch. But I've had students be able to do projects like this start to finish during the normal lab time. So hopefully we can still do that with all the cleaning requirements and all the fancy new things that we have to figure out in this brave new world of teaching, hybrid, remote, crazy chaos, whatever it is that we're calling, fluked learning, I don't know what we're calling it by now, but whatever methods we're using, I'm sure they're fun and interesting. So good luck, and if you guys still have questions, come and find me. This is fairly straightforward stuff that we're helping the students with. There's lots of tutorials and resources, and we want to point the students to, when you get stuck, which you're going to do and we want you to do, this is what needs to happen. So you go, you learn more information, you get stuck on the next thing, you learn more information, you get stuck on the next thing. This is the way they naturally learn from Gen Z. So this is something that we need to understand how to help them do, because this is what they prefer. So this helps them to understand better what we're trying to get them to understand, by letting them have the opportunity to learn, watch tutorials, watch videos, whatever they want to approach it with. All of those are acceptable. So good luck, and let me know if you have further questions.